Our aim is to design a water rocket system that maximizes the time to keep an egg in the air. We must ensure the egg shouldn't be damaged during the flight. Maximum launch pressure is 8 bar but can be varied. All parts must stay attached during the flight. We must make a simple design and can operate under a range of weather conditions, and it must be safe.
In a water rocket, thrust is generated when compressed air forces water out of the nozzle. This can be explained by Newton's third law. As the water is pushed down, the rocket is propelled upward. Impulse, the product of force and time, measures the change in momentum during thrust. The water fraction directly impacts impulse and thrust. Too little water reduces thrust, while too much adds weight. Studies show that filling the bottle to about a third to half of its volume typically produces the best results, as it maximizes impulse.
For a rocket to launch straight up, directional stability is very important. It is the ability of how well the rocket can move towards the direction where its nose is pointing. To get a better directional stability, we make the rocket symmetric in order to distribute the mass evenly and cancel out the moment around the center. To make the rocket more stable, we install 4 fins with a sweep angle. For example, when the rocket yaws towards its left, the air resistance experienced by the right fin will be greater than the resistance experienced on the left fin. The fins perpendicular to the other 2 fins will act as a vertical stabilizer. Hence, the air will push the rocket back to point along its path.
When it came to the parachute making, we had to consider 4 different aspects: the size, the material, the shape, and aerodynamics. First of all, we designed our parachute with a 60 cm diameter for optimal drag and slow descent, without adding excess weight. It was made from non-ripped nylon, so that it's lightweight and durable. It had a circular shape that helps maximize stability and drag. And finally, to prevent spinning, we added a circular vent on top, allowing smooth airflow and reducing turbulence for a controlled descent.
The nose cones and fins of a rocket are designed to minimize drag and provide stability which keep it pointing in the right direction without wobbling. According to Science Learning Lab, if the speed of a rocket is less than the speed of sound, rounded nose cone is a better option than a pointed nose cone. The reason we choose to use 2-liter bottle was due to several reasons. First, it has a larger radius which provides greater stability. Also, it contains greater volume of water compared to smaller volume bottle for the same water fraction, so it provides greater thrust. As a result, it will reach a greater altitude and less deviate from the ideal flight path.
According to the simulation, we found that the higher the fins are installed, the lower the rocket goes and stays shorter time in the air. Therefore, we decided to put the fins closer to the nozzle than to the nose cone to maximize the benefit.
Our project teaches 3 things: stability and aerodynamics matter for higher flight, weight and balance help protect the egg and ensure safe landing, and team cooperation is key to finding the best solution through efficient communication.